Today we have the last lecture. I should not have this. The last lecture on Outlook and to modern tools and a bit of a summary of what is possible and what limitations and what is stuff which I've learned over the years / which might be useful for you in a grand scheme of things. So we have gone through every different design process essentially, which you normally will encounter unless you work like in a modern environment, and about those tools we will look into now or today. So there's some questions. Basically, we're going to go in the slides directly through those questions. What other technologies do we have? What technology trends are coming with that? What challenges do we have? We have most of it's just a summary mostly. And open source software. What projects are there? What roles do they play? What lessons are there to be learned from those? How is the step from FPGA development to ASIC design? I'm going to go there not too deep, but there's one fundamental. And if you don't do FPGA development, what can you else do with the knowledge you learned here? Or when you do not, let's rephrase it, when you do not want to do hardware design on a low level. So from other tools, we have like neural network accelerators. I think that's probably one of the biggest hypes in the domain. Xilinx has spent significant resources on developing their tools. They bought a company. They announced it big time. They do quarterly or half-yearly updates on the documentation and on what they support and so on. And just to talk about this briefly, there's two kinds of architectures. I also name them sometimes a bit different, but one is data flow architecture and one is the overlay architecture. One of them, I call them also direct mapping, so into the logic, the neural network, or an accelerator. And what this means is that these tools, to the grand scheme, put the neural network or different design building blocks of the neural network into logic directly, and then you run from the neural network input through the different layers in logic directly and get the output out. In overlay architecture, you have an actual accelerator like a CUDA architecture or whatever accelerator which has convolutional cores, all the different cores, and then you load the weights, the biases, all the data you load on each cycle you load into your accelerator. And this one, they are mostly or vastly directly in the logic. There may be some, if the networks gets too big, HLS form ML and Fin have solutions that they basically will load some configuration, whatever they need, because the logic would not be sufficient to contain the entire neural network. So these two architectures you have, and they vastly differentiate between data flow architecture having, well, it depends on the network size, right? If I have a very tiny neural network, then I have an accelerator overhead, which I will not fully use. But the idea is that this is more resource intense, but has a very, very low latency and a huge throughput. So you can put the entire logic of an entire big network in there, and you will have a performance which outperforms CUDA. There's research which shows that just because you have dedicated logic doing it instead of general CUDA logic, and that of course is then more efficient. The overlay architecture is CUDA on FPGA if you want, so as a comparison. Not directly, right? Different architectures, different accelerators, different logic, but essentially this, and then you of course have your normal FPGA overhead, but it might still be viable because you have then a neural network accelerator in FPGA, and you can dimension this accelerator as you want, and then you can put other logic next to it. So you can put directly a signal encoding or whatever you want, or a controller for your sensor or anything you can put directly into the logic next to it. And that's of course something which you cannot necessarily do with another ASIC because you do not support the sensor directly. That will be a bit slower, mostly because of memory bottlenecks. So you need to transfer your data, all your weights and biases out of the memory into your accelerator on each cycle of your operation, which of course takes then extra time. Yes, and overall, there's more tools, and there's many more. There's a lot of academic research. That's what I mostly did. There's what the leading tools are in the data flow architectures or in the direct mapping into logic. You have Fin, HLS4ML. This from CERN, a huge initiatives. This from AMD Xilinx, and then you have from MathWorks, MATLAB, Simulink. They have very good HDL or FPGA tools for chip design as well. And this is nice because they integrate this fully into the overall workflow. So you can have your neural network for signal processing, which you design for your Simulink application. You can put that directly into FPGA without much extra work. Or at least that's what we sold. I've not tried it out myself yet. I've just seen it in demos. It looks pretty good, but of course the reality might be constraining, as we've seen in many, many tools. The same for those tools. Fin, for example, will only work with certain devices. So with processors, system on chips, so Sync 7000, Ultrascale, and Versal, I think. And HLS from ML is also, unfortunately, at least last I looked, constrained to Xilinx AMD devices, because they use, basically they synthesize their neural network into code which is HLS compatible. So basically synthesize it into that level, and from then the HLS tool takes over and synthesizes it. On the overlay architecture, that's something which came or kind of emerged in 2019, 2020, 2021. There was originally, I forgot actually to list it here, OpenVINO, which is an open source tool mostly supported by Intel, or I think even owned by Intel to a vast part, for accelerators in different domains, not only FPGAs. And of course then this allows you also to make an accelerator for neural networks on Intel devices or on other graphics or ASIC devices. In the scheme, which is very, very well known, you have AMD Vitis AI. And that was bought by, I don't know the company anymore which developed it originally. AMD just bought the IP of that and basically integrated it into their portfolio, where it has a lot of applications. What is good here to know also, again, this one, just for context, this one needs, but these days in the past when it was original research, so this is R&D project from AMD Xilinx actually. This didn't need in the beginning a processor, now it does. This one didn't need a processor, this one doesn't need a processor, and those need a processor for the control. So the processor controls the accelerator. What you can of course do, you can always put a soft core in there, but what has to be known is that a soft core is always going to be slower in the interface and implementation than an actual processor in logic. So it is really, and you have a big performance loss. It's really recommended to use all these accelerators if you somehow can with a system on chip. Otherwise, you will have by magnitude less performance or something like that, just because of the communication bottlenecks. So there's, for example, a space-graded version of Vitis AI, but it's on a pure FPGA, and that's just much, much slower. Microchip vector blocks is the microchip alternative to this. Nano Explorer is also working with the academia in Europe on an accelerator, where there's various proposals, and of course in other ASIC designs there's now neuromorphic developments and what other topics you may consider. What all of this has kind of together is all that they're all original from R&D projects. R&D project, I mean, I guess over the long term developed based on the backend that they have a synthesis tool. R&D project, and this was also an R&D project. So you just go from the always R&D project which get matured and then bought by companies. They were all at some point a bit separate or by the research labs of the company. So that's on the neural network accelerators. Every other accelerator may work quite similar, but because of the neural network hype, of course, that's where the most of the money is in there. What is nice here, actually, you may not need any FPGA knowledge to run those, but you will need some to make your custom firmware or add other stuff to it or whatever, or actually run it on a custom device. There's very good demos for certain series. If anyone wants to ask, there is university programs from Xilinx to run, for example, Vitis AI directly, very simply. There's also very good tutorials because there's such a huge interest from people to do this. Then we come to heterogeneous computing, which I guess is kind of why this FPGA topic becomes more and more relevant. You have CPUs, GPUs, or whatever ASIC you might want to call it, or other hardware accelerators, and you have FPGAs in here. And this all goes into the direction that over the last years, I don't know how many years, 10 years, you probably have heard of Moore's law that basically says that over a certain time, the silicon will get smaller and smaller, and thus the performance will increase. But as you may be aware, this has kind of not stagnated a bit over the last years. I mean, for a long time we were stuck with 14 nanometers. Now we're down to 5, 3, 2, whatever nanometers. So it's progressing again, but it's just a matter of time until we reach again manufacturing problems or limitations. And when this didn't anymore progress so fast from the low level silicon, people look more and more into ways to accelerate or get more performance out of the chips in other ways. That's why there has been such a huge development in new chip architectures, because x86 worked always and always got faster when your silicon gets smaller, but at some point this didn't happen anymore, so people looked into other areas to optimize. And overall chip architectures is just what happens. So what people realized is, okay, my CPU is very good in general stuff, but it really doesn't accelerate anything else. Then they looked into GPUs for graphic stuff, which was originally already needed to be enabled. And later, over the last, I don't know, 5 to 10 years, I've seen an insane amount of hardware accelerators. You have seen from, or maybe you are aware of Facebook, Google, whoever, I think Tesla as well, is on every big company with a lot of market cap have developed their own chips to accelerate their task. And this is, of course, something which then goes into heterogeneous computing. They have their own accelerator for their logic operation, which they need, and they have the market cap to make their own ASIC. If you do not have the market cap, you will go for an FPGA, or if your application is just too diverse, if you would need too much logic to cover all your different, or too much silicon to cover all your different logic circuits, then you will go for an FPGA, and I will come to that and reconfigure your device. The FPGA role is here because of your flexibility, potential energy efficiency, because you can really optimize to something which you can't do to others, and then performance through the dedicated logic, which basically is kind of trying to avoid the plateau of Moore's law and still have a performance gain, even though my silicon itself does not get more performant. Then there's a technology which I find quite fascinating, especially in the space domain, that changes a lot of things. It's dynamic partial reconfiguration, or at all reconfiguration in space domain. In the past, and especially when there was very well-defined, high reliable projects or space probes, we never reconfigured our FPGA. We used like FPGAs which you programmed once, and that's still the thing. You program your FPGA once and that's it. You never reconfigure it, you never change it. And that's how it works. In cloud computing and in other domains, you have trends emerging and space also that you start reconfiguring, because it gives you just so much potential to change your logic later on in the mission. It gives you can reconfigure or partially reconfigure your FPGA, which in this case, just to stick to the very detailed one, or to the newest trend, is that you can do this during runtime. So you can have your FPGA still running with whatever accelerator you want. Maybe I have a neural network accelerator and I want to run a different neural network, right? And I have a setup where, or I need to have a different video encoding or signal encoding or whatever, switched it during runtime. Then I can just switch part of the logic and reprogram only the part of the logic. And then I still have the rest running, and then I can switch to the other accelerator and reconfigure the rest or whatever. And I never have a downtime, which of course can be quite nice. And especially it is useful if I have important logic still running on my FPGA, and I do not want to, or I can't switch it off, because then I would lose everything, right? So I need to keep a part running, and then I can at least reconfigure the rest. Basically, enable switch between different configuration-based required tasks as video encoding or whatever. It's especially interesting for frequent updates, for frequent updating tasks. That phrasing was good. Basically anything from video encoding to neural networks or Internet of Things tasks, those kind of things. So really edge processing, where you really need a lot of performance and a lot of flexibility. And of course, and this is basically where this becomes even more important for FPGAs. When this technology becomes common, FPGAs become more powerful in this domain because it's something an ASIC or so can never do. And someone might want this flexibility. And overall, FPGAs get less and less into the high performance domain because there is entities like big tech companies which can afford to make their own silicon. But still the same applies, that they are still expensive to do your own ASIC or to do your own tape out of an ASIC. And an FPGA will just have a lot of flexibility, or it may even be entirely impossible to have an ASIC because you cannot change your application just quickly during runtime. And you're never gonna get the flexibility with the performance with any other chip type than FPGAs. Applications, real-time video processing, AI system, of course, or mission-critical applications where I can never have a downtime or never a failure, essentially. Also, of course, possible if I have redundancies and I realize I've bit flipped whatever in one part of my logic and I have a voting system between my different logic circuits, then I can just reconfigure a part of it while the rest keeps running. But this becomes very, very complex because you then have to think what happens on this failure, and you're adding a complexity layer on everything. You need to basically then ensure that my reprogramming doesn't lead to a failure state. Why it is, for example, critical in space missions. When you reconfigure FPGA, there's a chance that you get stuck in a reconfiguration state, and then you can't get out of it anymore easily, and then you're like, yeah, I reconfigured, I want to get more performance, but I have nothing anymore. For another technology, especially towards open source and democratizing developments, is RISC-V. I don't know who has heard of that. It's a processor architecture. It's after x86 ARM. It's the next rising architecture, especially in the domains of open source and no licensing. Many companies were really annoyed about the ARM licensing at some point. Well, they came up with RISC-V and said, we don't need that. RISC-V is very, very flexible. It's openly available. It doesn't have any licensing fees, no royalties, and you have basically full freedom to do whatever you want. It is mostly, however, used so far I know a few devices I've heard of, and I know of one device which uses RISC-V now, actually in the space domain. And it basically, what RISC-V allows you is rapid prototyping, but most importantly, cost-effective innovation. Because it doesn't cost me any licensing, I don't need to have any contract, anything. So I can just do my FPGA design and rapid prototyping, and then maybe even put it into an ASIC or whatever, and I'm just done. I do not have to deal with anyone else. And of course, the scalability is nice because I do not have to pay already when I have a small. I do not have to do any licensing or whatever, only when I have like 3 devices a year produced. So this is quite nice. Applications here are very much low-cost technology concept developments. So I can just use whatever I want here. Academic and research, just to explore different access. So RISC-V also is a very flexible architecture. So it allows you to very easily integrate different accelerator technologies or different dedicated logic circuits or whatever. So that you can integrate neuromorphic or whatever you want fairly easily. And of course, this is then very nice for technology concepts, academic research. And of course, the processing system market, that's what I'm going to call it now, everything in the chip market is expensive. And something like this, of course, lowers the entrance threshold to get into this market. So you can afford easier to get into those markets. And that's also where FPGA plays a big role, is because if I can prove my system on an FPGA and I can make an FPGA reliable and so on, I may get the resources or the funding to actually use whatever I have tested out here to put into an actual silicon, into an ASIC tape out, and then I have a lot of R&D and money saved, and I actually have already a proof of concept, and I can say, this is what I get on FPGA. If I have an ASIC with this technology, I'm gonna this and this much more performance. And I have a stage development. I do not need to do everything at once, which brings me to almost on the slide after this. Which brings me basically then to ASIC development. I'm gonna come to that in a second. FPGA is more than challenges. I mean, we have talked about those quite extensively in all the different parts of the lectures. Scaling and complexity with our bigger and bigger design, the devices get bigger and bigger. Also, the time enclosure and the routing capabilities get challenged again, right? We have, when we think about device from 20 years back, then we have routing algorithms which struggle with that logic. If I put that same logic on a new device, I will not have a problem, but then again, I have so much more space on this device, so I can do so much more, and then of course, the problem gets bigger, and then my tasks are being challenged. Most importantly is here, and you really see this when you work with tools from years ago or from various vendors, you see when you push the performance, you see really the difference in the algorithms, even though you have no idea what's happening in the algorithm, you will see the difference. And the other one is the advanced high-level optimizations. So if I talk about HLS, so there is always continuous development ongoing on making a better rollout, making better pipelining, giving easy options to optimize my hardware, and all these kind of things. And then, of course, power and energy efficiency. There is always the question of what approach do I take? When do I do an ASIC design? When do I do an FPGA design? An ASIC design is when especially when you have the resources, and these are again on the one hand side, the FPGA resource requirement goes down because with all the tools, but it's still a learning curve. We're going to come to that. But also we can go to the top, so we can optimize much more. And the ASIC at the same time also comes down, and of course also goes to the top. So the gap may be getting smaller and smaller for certain applications. But simply put, if I need the flexibility, it's FPGA. There's no debate about it. And an ASIC design will only be relevant if I have the money for it, or the quantity to justify the money. So for example, on the big tech companies have done their own ASIC designs because they spent, I don't know how many $1 million on this, but they spent more money on power consumption. And their ASIC designs basically reduce the power consumption of all the server centers, or even enable certain applications. So it's just worth alone the power saving costs which they have through their own design is so big on the big server centers that it's worth to do this. Or of course for others it's like, for someone like Apple or so, it's their own silicon enabling to their own ecosystem just fits better. And if they exactly know, Apple has such a constrained and closed ecosystem that it just allows them to make the perfect chip for whatever they need to do, which of course is very, very useful. And then will leave everyone else behind unless they have also their own ecosystem as enclosed, and so on. Toolchain limitations. I mean, I think we have talked about this. The learning curve is, of course, I think that's why we're in this course. The proprietary tools, yes, there's a different challenge. There's just so many tools which cost really expensive licensing. You cannot access what was happening on there. You can only use them with certain devices, and that's really, in my opinion, when you have learned once, you may have still to go through the different tools, and then you have a learning curve for each of the tools, which is kind of annoying. And then, of course, integration limitations is that not each of the tools integrate with each other, kind of what I said. And basically, there's open source initiatives which try to access a wide range, but may not always be the case. There's not a real solution to this right now. That's why there's essentially one solution is to look at the market. There's so much happening right now in FPGA in the chip design domain because of Internet of Things, and in every car, everywhere, there's chip design in there. So the market is developing so quickly, and it's also opening up slowly. So it's better than opening, not at all. So there's a lot of initiatives. And we're going to come to that in the open source topic, which is, of course, a different discussion. And still to this day, it's the market accessibility. It's just that, as said, the toolchain limitations go into the market accessibility. If you cannot afford alone your tools, how are you, when you have 100,000, 200,000 euros as a company to fund, and that's already a lot of money, right? The license for one of those may cost 40,000 euros. So I have my labor costs plus a tool, which is really, really expensive. So it's just something which may be difficult for small companies or small teams. And the workforce is also expensive generally because it's a very specialized field. And basically this hinders small innovative teams when they have an idea really to get that idea to market. It's very difficult. But we have a hope there is that such things like RISC-V has already enabled a lot of initiatives. And that, of course, RISC-V can also advances open source initiatives, and that goes back and forth with each other. So RISC-V is an open framework, and that allows you to easily integrate open source tools. Certain companies have also started their open source initiatives because they've realized that open source is not existing in this field. And of course, they are being loved by the community for that at the same time as they get a lot of R&D input and ideas. And they want, let's put it this way, an FPGA company wants that the FPGAs are being sold more. How do I do this? When I look at workforce and toolchain limitations, then the easier it is accessible, the more I will sell. And then making it open source is just a big, big advantage. I do not have to make the full tool open source, which brings us to open source. There's one thing. I will talk very briefly about each of them a bit, maybe, hopefully. There's one thing overall in open source, and especially in chip design. It's that there's a lot of money there. And when someone does good research, someone wants to buy it. So what has happened is, and I want to list here actually tools, is that there's a tool which went actually up to leg up, version 9 or something like this. Leg up was an open source HLS tools, wonderful. Suddenly, and actually a lot of workflows, also for neural networks, started to rely on it. And I discovered this because I found a research paper from a year or two ago. I was like, oh yeah, that's really, really cool. Let's do that. And it turns out that the entire backbone, so the open source tool, the HLS tool, for my neural network accelerator tool, which I wanted to use, was bought and acquired by Microchip and just disappeared. And a few months later, Microchip had a better HLS tool. So they see that the open source or the academic market is well developing, and there's a lot of money in there. That's also how it's meant to be in a part. Academia is in constant talks with the industry usually when they do these initiatives. And they basically just waiting for the maturity for a company to take over and give them back the millions they have invested in labor force, which is, of course, that's how research works. Right? We do in academia early stage developments, and we rarely make the market ready. So at some point, someone has to swoop in and acquire the technology. And we have done a lot of these different technologies. That's what research is about. And these activities are usually that big that we make them these days open source, because then we have contributors from different directions, and it makes collaborations easier and all these kind of things. Just to go through the tools, GHDL might be very nice for you to use if you do not want to go into synthesis or just want to learn a bit of VHDL. GHDL I used, actually I was used in my course where I learned VHDL coding itself. However, whatever can be simulated in GHDL may not be synthesizable. It's not a complete tool, if I understand correctly. And let's put it this way, if you can work with ModelSim or with Vivado or whatever, and it's not too annoying, then why you use GHDL? It's a simulator, it's a nice tool, but it has its limitations. SymbiFlow is a overall almost end-to-end tool chain, which basically takes FPGA, well actually only Verilog code in and puts that to the end until actually bitstream. So, and that will take in the backend tools, the synthesis tools like Yosys, also an open source initiative. However, what is always common, I mean, and it applies the same for HLS, actually for Bamboo HLS as well. For Vitis, I will come to it in a second. They all, I mean, GHDL will less, but here specifically when you come onto, when you Google it, the first thing is come. It's a good tool, but the workflow might be quite challenging to achieve. Which is an open source tool, not as well documented, a lot of patches, a lot of different things, settings which you need. It's not as widely adopted, not as widely tested, not every bug or whatever is fixed. So it might take you a significant effort to get it running, but in the end you have an independent workflow, and if you mature it, you might be able to integrate it into your own tools, right? So it's something worth to consider. Bamboo HLS is actually a European initiative. It's, in my opinion, the best HLS tool which is open source out there right now. And well, it's under GPL3 license, but there have been talks that it may be acquired, may get acquired, but then everyone said, please don't. And we do not have intent to sell it, so maybe it's some licensing which happens to some company or whatever, but the tool itself hopefully stays available open source. I don't want to say a wrong date, in 2021 or 2022, I think it was. 2021? Yes, in 2021 actually. Just when I was actually doing my master's thesis, Xilinx was like, hey, here's free access to our Vitis HLS open front end. And basically it's the parts, and that's something which I've not covered in the HLS course in the lecture, is that every HLS tool will convert the C code into something intermediate and then put it into low level or whatever level the output is. So it's a so-called intermediate representation. So what Bamboo and also Vitis HLS actually base on, they convert their C code with certain compilers and certain additions and so on into LLVM. And the LLVM can also be used in C backend. And so basically that's where the overlap is, and then they just build a backend from LLVM, low level, I forgot already what it is. It's a low level and intermediate representation, so between languages are representation, so languages of languages, if you want, so kind of. And basically then this is from this intermediate representation, even if it's in binary, they take it out and put it into VHDL or whatever comes in the end. It's also being used actually not only for FPGAs, it's used for CPU architectures, for GPU architectures. So if you understand how to do these things, then you can actually suddenly develop acceleration or from one domain to another one. And what I, for example, did is actually, why I came across both of the tools was because TensorFlow XLA uses in its backend, dumps out LLVM. And then I suddenly had an interface from LLVM to something like Vitis. Of course, Vitis made accessible the open source front end. Well, it's an input, so you code it and you write and you got LLVM out. But of course, the backend I didn't give out because that's where all the money is, let's be honest. From LLVM to effective VHDL code is a big thing because the front end from C to LLVM is needed for CPUs, for a lot of other domains, so there's stuff existing. That's not where the expensive stuff is. And so what has happened is, and also for OpenVINO, that there is an open source initiative which opens the market, but only as far as it benefits the companies, right? Of course, which makes sense. I mean, you have still a business case and all these kind of things. And to be honest, Vitis HLS is accessible for anyone for free, kind of, as long as you are a friend of the US, I guess. And that's how it is. And basically, as long as you do not go under export restrictions, you have access to Vitis HLS, at least to a certain extent. And at some point, you may need some licensing, but that's okay. And then, of course, new network accelerators. This one bases on, well, Vivado HLS or Vitis HLS, so they are together. This one is our own research lab. And there's a lot of open source other neural network accelerators from academic papers. If you go into FPGA neural network accelerator, you will find hundreds. There's entire papers of pages long which do a review of just the different initiatives or different ideas people had. So this has been, the accelerators have been in the works since you can imagine. Probably CUDA also has somewhere in the back. and some academic work from like 15 years ago. As I have been asked about FPGA and ASIC, I will not go into tape out, into the process. However, in general, I think I made it clear over the course, the shared concept, the design flow is very similar. So from HDL design, how you write it, of course, we assume here now similar to FPGA, not like very low level silicon. Because I've not encountered that, I cannot say much about that. But HDL design is similar, simulation and timing. The challenges are similar, of course. You have, instead of FPGA logic, you have silicon level simulation, and also the verification is done in a similar way. So you have the similar steps. So you look in place of routes, timing, and all these kind of things. But the big difference is that you need, for an ASIC design, it needs to be perfect and optimized. Well, it does not have to be necessarily optimized, but why are you doing an ASIC when you're not optimizing? The challenge here is really that you have an expensive tape out, and you need to make early stage very clear and very sure that your design will work. So you may actually use an FPGA for rapid prototyping. And then when you know that your logic works, you may want to look into FPGA stuff, into ASIC stuff. So that's a big, big difference. The overall workflow, they are overlapping the limitations, the logic problems, the bus systems, whatever we had, IP cores, all this kind of stuff is very similar between ASIC and FPGAs. So that's something to be aware of. Of course, there's going to be different tooling. But if you use, for example, Catapult from Siemens, then you're using an ASIC FPGA tool. And then you're going to find model sims also being used for both of it. So you have a very big overlap between the different domains. Use cases, FPGA for rapid prototyping and flexibility. I think we had that extensively also in this lecture. FPGA reduced time to market for ASIC. So I can do rapid prototyping and try different things. And then when this works, I have tested it out, and I can already sell the FPGA IP core while my tape out, while I get revenue in to finish my tape out of my ASIC. And basically, ASIC you always want to use for highly optimized designs with sufficient production numbers, or where these overhead costs do not matter, or where ASIC is my only solution. I need to be this optimized, and otherwise I will never get the performance I need. Often in security and defense, a domain, there's money, certain solutions you want to get ahead, then you will do your own ASIC design. Or for certain motor controllers in cars or something like this can be a thing, where you have really high production scales again. FPGA development and as a stepping stone to ASIC engineer. That's simply how you can put it. If you look at the workflow, there's a simpler version of FPGA for HDL simulation, timing. You do not need to go so much into depth. If you are a good FPGA developer, to a certain limit, you will just be able to level up in a certain direction and do your ASIC design. Of course, when you become very, 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 very good in FPGA, then you're getting away up it again from ASIC because you have so many advantages. Good. That would also cover that. Let's see if I have something else. Yes. Just to close this, I think it's the last slide of the lecture, or second is last. What else can you do with the knowledge you learned now? It's just a selection. You can always come to me or whatever, or ask to Sten to ask about tasks. The big thing which people always forget, there's FPGA developers, but these days, especially with system on chip, what comes to that is also developing your own drivers, your application software, all these kind of things. And of course, if you understand a bit the back end of a hardware accelerator a bit better, you will have an easier time writing your driver. So driver and firmware development, if you do not like the hardware development, you have on the processor side the integration part. You can also utilize programmer logic in so many other ways with the modern tools. We had the hardware accelerators. You can use it in Vitis AI, OpenVINO, and in Pink or Python Sync. where you basically have different IP cores and you just actually write in Python and this will reconfigure your system on chip. But of course, understanding hardware acceleration or the FPGA design a bit will be useful for this. But you wouldn't need more than the course to. I think for all of these, you do not need more than the course. You can run Vitis AI on your own chip with this, or Vitis AI, or Fin, or Python Sync, or whatever you can run in there. It will also allow you to hopefully select the right processing platforms for the different tasks which you want to do. I hope I gave a bit of an insight into these things. So what downsides does every processing platform have? What is useful here and there? You can always, of course, do open source projects if you're bored. If you have a lot of time, you can, also, of course, always go into open source projects. But honestly, I was joking, I mean, of course, if you're bored, but this year is where you learn so much. As in any other domain in programming or like processing or whatever it is, going into open source projects and being active in the open source community is cool for the open source community, but it actually teaches you so much because you get an insight into how things actually work. And that's something very useful. I learned when I was active in this, I learned a lot. I learned more than in any other projects because you just get confronted with so many things from different angles, which is quite useful. And of course, what you can do here is that you can always, with the academic, these tools should allow you to get into the academic research. So chip design, network accelerator design, all these kind of things. What you learn in this course is already sufficient to, for example, develop your own or start developing your own network accelerator for FPGAs with what you learned here, because you have learned various steps. So you do not need to do VHDL coding. You can build your tool to avoid VHDL coding if you want. Then last words. That's the last slide. Basically, FPGAs have a huge importance for versatile processing system, which will further increase. I've mentioned it in cloud computing, different reconfiguration options to get it very flexible. And then don't be hesitant to try new trends. I have heard in various, when I got the I tried this 5 and 10 years ago, I'm not going to try it again because this approach never worked. Yes, fair enough, you don't want to sit there every 2 weeks and try the newest tools, because then you won't get anything done. But be open-minded, because this is where a lot of money is in there and where a lot of people try to advance it, because everyone wants to get these things quicker to market, easier solutions, and that's something to be open-minded about. If you have any questions about anything of this or what we have discussed before, you can reach out to us for any kind of project, internship, collaboration project, thesis, or developer with us is also possible, or with companies which we know. And then I have a last word from ChatGPT. It's beautiful. And in a rapidly changing tech landscape, FPGAs offer the freedom to innovate, adapt, and thrive in the face of complexity. Everyone is scared of FPGAs because they're complex, but they will also challenge you and may help you advance. Good. That should be it.
Beautiful speech.
Right.